And do I do the share screen then?
Yep, go ahead and share the screen.
Okay.
So we are lucky to have Jay Lockman back with us today. Yesterday, he kind of gave us a broad overview of radio astronomy science areas. This morning, he is going to give us a talk about some of the history, present, and future of radio astronomy. So go ahead and take it away.
Thank you. Let me see if I can. I think if I can move the. There we go. Okay. I'm trying to move the images here so they don't block what I'm seeing. Well, they do. I can't do anything about it. All right. Thanks very much. I just want to go through a little bit of the history of radio astronomy. It's interesting, and a lot of it is still going on in the way, and I've been asked to talk about it. I had to learn about this a couple of years ago for some other work I was doing in another venue, and I apologize to Savannah Carey, who is probably going to have heard all of this before. But let me jump right in and talk about the initial discovery of radio waves from the universe, which, as I mentioned yesterday, was by Karl Jansky, a young electrical engineer working for Bell Labs in Holmdel, New Jersey. And he had this very unusual looking antenna that scanned the horizon, I think once every 20 minutes, driven around on a couple of Model T Ford wheels. And it looked about 5 degrees above the horizon and scanned around looking for very low frequency radio waves. Is the chart below being blocked for you?
No, we can see that.
Okay, great. All right, just blocked for me. And anyway, he discovered this pattern of radio emission that was fixed in the sky. The news made the front page of the New York Times, and you would have thought at this point that all of the astronomers in the world would have stood up and taken notice, but they didn't. And it's a really interesting reason why. And one of the reasons is because here is where Jansky's experiment stood in terms of frequency on the x-axis and then kind of brightness on the y-axis. And there are the familiar Planck curves there for objects at room temperature and hotter. But Jansky's emission was clearly coming from something that was extremely bright at very, very low frequencies. And there was no physical mechanism that was understood that could produce this. And not only that, Jansky's work was coming out of kind of electronics and not obviously connected to astronomy. And so the existing astronomers really didn't know anything about work at these frequencies. There was no model for what the emission could be. Jansky's work, as I said, was coming out of engineering. So it was neither fish nor fowl, and kind of lay fallow. And then along came one of the most interesting people I've ever had the privilege to meet, Grote Reber. He was shown in 1940, and he was a young engineer living in a suburb of Chicago and was interested in Jansky's work. And so he asked around to see if anybody was going to be following up on it. And when no one did, Reber decided to take matters into his own hands, and he built the first dish. He built this in the vacant yard next to his mother's house in Wheaton, Illinois. It was a suburb, and did all the design work himself. A lot of the fabrication, he paid for it out of his own pocket. Remember, he was in his mid-20s, early 20s, and got it right. It's pretty amazing when you look at this, how familiar this looks. There weren't a lot of dishes around at the time. I'm not sure there were any dishes around used for communication. But one of the things that Reber understood was he understood the blackbody curves. And so if Jansky was seeing something at 22 megahertz, then if he looked at his highest possible frequency he could, which is 3.3 gigahertz, then he really should be able to see something. I mean, all of the curves increase going to higher frequencies, to shorter wavelengths. So Reber designed his dish. It was a transit instrument pointed north-south, but not east or west, and built receivers at 3 gigahertz, detectors at 3 gigahertz, everything else he did. And he got nothing, absolutely nothing. Well, here's another image of his dish. And if you look in the lower right-hand corner, you can see a white picket fence. This really was, oh, let me go back up to this initial picture here. This is from a newspaper. And unfortunately, okay, he says, what is this? All Wheaton ponders the purpose of this 3-story mystery contraption erected by Peter Reber. Even got his name in his yard. Airplanes would buzz it. It was really quite a remarkable thing. Anyway, this is him. He rebuilt all of his equipment to work at 900 megahertz and again struck out, got absolutely nothing. And at this point, Reber said, more normal people would have been discouraged, but I took it as an increasing challenge. And he rebuilt his equipment again. There's him in later years, him at the top standing by his focal point of his dish. He went down to 160 megahertz and got a detection and started mapping the sky. These are some of the chart recordings that he produced. We've got a lot of Reber's original equipment here in Green Bank. He would summer in Green Bank during the last few years of his life. And this is very interesting because you see this pattern of the Milky Way passing through the beam of his telescope. And you also see all this hair on this fuzz. That's interference from passing automobiles. And the interference environment in Wheaton, Illinois was so bad in the late 1930s that he ended up having to restrict his observations only to the nighttime. When you draw the spectrum between Jansky's measurements and Reber's measurements, here's what you get. And that was what so confounded people. And as I mentioned yesterday, it took 20 years for physicists to understand the source of this radiation. But spectral index was completely opposite of what was expected from a normal black body. In the late 1950s, Reber brought his dish, which by then was equipped with a turntable so it could move in azimuth, to Green Bank, where he supervised its reconstruction, and it sits today. It's pretty remarkable that one guy, very stubborn and very persistent, could pull such a thing like that off. I'm sure, Jim, did you meet Grote?
I just missed him, unfortunately.
I don't think anybody who ever met him ever forgot him. And I think he was the inspiration for the tater tots scenes in Napoleon Dynamite. It's a remarkable guy. This was the kind of maps that he made. And here you're showing a map at the top at 140 megahertz of the Milky Way and below at 440 megahertz. And if you can see the scale, you realize that at the lower frequencies, the radio emission is much more extensive and brighter. He published a paper in 1944 called Cosmic Static. A disturbance in nature manifests itself as electromagnetic energy in the radio spectrum. And he talked about also measuring something from the sun. I want to mention a third pioneer in radio astronomy. We have Jansky, we've got Reber, and here's Ruby Payne-Scott. She was an Australian and was called the most talented mathematical physicist in Australia at the time. And this was in the 1940s. She was involved in the Australian radar effort. And here's an example of the kind of antennas they were using. And here's a photograph of their installation outside Sydney Harbor. The harbor itself is the inlet on the top center. You can see some ships about to come in. And she and a group at what was called CSIRO, Commonwealth Scientific and Industrial Research Organization, developed Australian radar during World War II. In a bit of brilliant management, the Australian authorities at CSIRO decided after the war they wouldn't break up this very talented group of engineers and physicists. Instead, they said, find something civilian to work on, and they all moved into radio astronomy, Ruby Payne-Scott with them. And they started putting antennas up and measuring, discovering, in fact, these bursts of radiation from the sun. So Ruby Payne-Scott was the first woman radio astronomer and also the first woman doing radio astronomy in the Southern Hemisphere. These are the three pioneers I've just talked about, and it's interesting to consider what eventually happened to them. Jansky was always rather fragile health, had fragile health. And in fact, the only reason that he got hired by Bell Labs was a relative pulling some strings for him. He failed the basic physical exam for employment at Bell Labs, and he died at the age of 42. But at his death, radio astronomy was just taking off. And so it's pretty certain that had he lived another decade to see what became of his discovery, he would have gotten the Nobel Prize for it. In contrast, Grote Reber was always a loner. He lived into his 90s to see what had become of radio astronomy. He hated the thought of big science, big establishments. In fact, while he was here one summer, he tried to talk NASA into giving him a surplus intercontinental ballistic missile so he could launch some hydrogen into the ionosphere and create a big neutral hole so he could look out at very, very low frequencies, and just didn't understand why they just wouldn't turn a rocket over to him. He lived in a remote part of Australia and, as I say, died in his 90s. Ruby Payne-Scott had a different fate because while she was working for the Australian government, she committed a very, very serious breach of rules, which when discovered caused her to lose her job and to forfeit her retirement. You see, she had gotten married. And at that time, the Australian government said, the rules were very clear. They said any woman who marries immediately forfeits her position. Her marriage was secret. Her colleagues at CSIRO knew about it, and they shielded her. They kept this quiet, but eventually some bureaucrat found it, and she was forced to leave the field. A couple of years ago, the New York Times realized that since 1851, its obituaries have been dominated by dead white guys. And so they started a program to make up for the people whose obituaries they should have published. And there, in August 2018, came the obituary for Ruby Payne-Scott. An interesting coda on her story. In Europe, the discovery of Jansky and Reber were taken very seriously by Jan Oort. He was a prominent Dutch astronomer, one of the greatest astronomers of the 20th century, very interested in the structure of the Milky Way. And he realized that radio waves offered a way to peer through the dust. Because of dust, we can only see a few % of the Milky Way at visible wavelengths. But Oort knew that if we could find radio wavelengths studies, that it would allow us to understand the entire Milky Way and not just our little local area. He ran into a young guy named Hendrik van der Hulst in what was called the 10 Minutes That Changed Astronomy. And they had a symposium for van der Hulst's 100th birthday a few years ago, and there was a lot of discussion of this because van der Hulst at that time was a young man in hiding in the Netherlands. And what happened during World War II was that the German armies invaded the Netherlands. They started purging the university faculty of all Jewish professors. At Leiden University, the rest of the faculty resigned in protest. Oort went into hiding in the countryside, and van der Hulst, as a young man, went into hiding also. Had he been discovered by the Germans, he would have been sent to do forced labor somewhere on the Eastern Front. So a very touchy time. Oort nonetheless tried to keep up research and a research community, and there are stories of him bicycling around with manuscripts hidden in the air pump of his bicycle. On one of his bicycle trips, he got a flat tire, and while he pulled over to investigate it, he noticed that he was right near the Van der Hulst family farm, and he knew them, and so he went into a barn there where he could repair his bicycle and be out of sight. Young Hendrik came to see what was going on and had a chat with Jan Oort. And at that time, I'm told, the bicycle patch kit contained some abrasive material that you would put on the surface of the bicycle tube, and then you would put on glue, and you were supposed to wait 10 minutes for the glue to harden before you actually put the patch on. And according to people who were there, nobody ever waited the 10 minutes except Jan Oort. He was a very meticulous guy. And so while he was waiting the 10 minutes, he got to talking to young van der Hulst, who was interested in science. And Oort said to van der Hulst, why don't you do some calculations and find us a spectral line that we can do spectroscopy in the radio. And this is a reproduction years later of Van der Hulst presenting his results at a meeting in Leiden during the war. It was a clandestine meeting because, as I say, had many of these people been discovered, they would have been sent off to labor. But anyway, Van der Hulst predicted the existence of the 21 centimeter line of neutral hydrogen. It has a wavelength of 21 centimeters and a frequency of 1.4 gigahertz. After the war, Oort started pulling together surplus material and basically started a radio astronomy lab and tried to detect the signal from hydrogen. At the same time, Ewan, a graduate student shown here at a building at Harvard, and his advisor, Edwin Purcell, thought they'd give it a shot to see if they could detect the emission from neutral hydrogen. They knew the frequency quite well, but had no idea of what to expect for the intensity. And Purcell decided it was going to be non-detectable. And so Ewan already had a job offer. And so all he had to do was finish up this experiment, get his PhD, and then he would leave. And so they built this horn and stuck it out of a upper story of a physics building at Harvard. And there's Ewan with it. They built a very sensitive receiver and some switching systems to detect it. And Ewan was here for his, where is it? There he is in the lower right. We have the horn here in Green Bank. Ewan was here for the 50th anniversary of his discovery. And he said at that time, they were convinced it was not going to be detectable. And Purcell had told him that a non-detection has to be 10 times better than a detection to get a PhD thesis. So he really worked very hard, and they were very surprised when in fact they got the detection. Ewan said at one point he came back from lunch and he saw a group of the Harvard faculty standing below the physics building in the winter trying to launch snowballs into his horn. And he said the physics faculty could smell a failed experiment from a mile away, but it wasn't a failure. And in the end, they made a detection. They contacted Oort, who was put together some equipment very quickly and confirmed the detection and made some measurements of galactic rotation. And they sent the word down to colleagues in Australia who also detected it there. So those 3 detection papers appeared in the same issue of Nature. And up on the top left is a picture of Van der Hulst and Oort later on at a meeting. After World War II, the Dutch coast had a number of these Würzburg antennas. I believe they were 8 meters in diameter. That was the German war effort. And so you can see there's a person on the right descending a ladder. That gives you an idea of the scale. Oort and the group outfitted these and started mapping the Milky Way. And it wasn't very long before they discovered the rotation of the Milky Way. And a few years later, the International Astronomical Union moved the Galactic Center to coincide with what was known then. At the same time, this is an 11-meter dish, I believe, in Australia that was built for mapping hydrogen, and the Australians started mapping the southern sky in the early 1950s. Oort got himself a dedicated state-of-the-art dish here, the Dwingelo dish. It's located at a national park in the northern part of the Netherlands. It's still there, you can see it, 25 meters in diameter. And it was commissioned in 1956, and for a year was the largest telescope in the world. It made many discoveries in neutral hydrogen. If you ever worked on or will work on the W objects, W31, W49, that was a continuum survey done by Westerhout using this telescope. Meanwhile, in Australia, there were other efforts underway, and Bernie Mills built what is called the Mills Cross. It's a series of dipoles in a cross, and the dipoles in up one arm give you an antenna response pattern on the sky that's narrow in one dimension and fat in the other. And so you have a perpendicular arm that gives you a response on the sky that's fat in the other direction and narrow in the other. You combine them both and you get a reasonably good directive beam. A copy of this was built along the Potomac River in a farm just west of Washington during 1955 by Bernie Burke and his postdoc, Ken Franklin. It was a Mills cross. Each arm was more than 1,000 feet long. And you can see here, it's made of a series of dipoles, and you just combine the signals from the dipoles with the proper phase, and you get directivity in one part of the sky and not the other. And they were extremely lucky. This was an amazing example of serendipity, in that they were looking for, Cas A supernova remnant and the Crab supernova remnant. That's what they were trying to study. And they looked for some comparison positions. And at the position of their comparison position, which was chosen kind of randomly, they found these very bright, very brief spikes of radio emission. They thought at first it was local interference, but they realized that it was shifting through the seasons. And in the end, they realized it was coming from Jupiter. This was the first radio emission known from a planet, and it was bursts from Jupiter's magnetic field. It was also received quite a lot of publicity. Meanwhile,
Jay,
in England,
can I interrupt you real quick for a question?
Sure. Yeah.
So Casey was asking why neutral hydrogen was the main thing that people were looking for or looking at, as opposed to, I guess, some other molecule or another source.
Yeah, I mean, at the time, they understood that hydrogen was the most abundant element in the universe. And I must say, Van der Hulst considered whether one could look at ionized hydrogen as well. And the calculations suggested that the ionized hydrogen that I discussed yesterday, this capture and cascade lines, would be broadened all out of existence. They're very lightly bound transitions, and collisions with nearby electrons were thought to blur the quantum transitions to the point that the lines would be completely undetectable. And that view was prevailed until the mid-1960s, actually. Maybe it was late 1950s, when a Russian theoretician, Kardashev, predicted that the lines would be detectable. They were then discovered in Russia and the United States. But they went for the most abundant element, hydrogen, and at that time, interstellar molecules were completely unknown. Hydrogen is still the brightest spectral line, with the exception of a few masers. So this was a big dish built because they could. I can't even remember what the scientific justification of it was. It may have been to study meteor trails, reflections off the ionized trail left by meteors. As it was being built, the 21 centimeter line was detected, but that was right at the upper frequency limit of what this telescope was capable of. If you're interested, the story of Jodrell Bank is a really quite fascinating book told by Bernard Lovell, who was the person responsible for this. And amazing tale of engineering. Nothing like this will ever be built again. It's this huge lumbering structure. They just didn't have a lot of experience in building movable structures this big. It still stands, it still works. If you get a chance to go there, there's really nothing else quite like it. But that was then the biggest telescope on Earth for quite a bit of time. At Cambridge University, they were into interferometers. They were looking at, again, smaller antennas, in this case, a series of dipoles here that were lined up and cross-correlating the signals rather than adding them in phase. And this is the famous 3C aerial that mapped the sky and produced the third Cambridge 3C catalog of radio sources. But you can see right now, the pace of development is accelerating continually in the mid to late 1950s. Canada got into the game in 1961 with its 25 or 26 meter dish. In the background, you can see a number of poles there. And that was, again, a very low frequency array, I think in the tens of megahertz, that was modeled on the arrays that were around the world in other places. This was taking advantage of the good ionospheric conditions in Canada and its coverage of the northern sky. In Australia, the Parkes dish, which is still producing wonderful science, was commissioned in 1961, 210 feet in diameter. And here you can see a kind of composite surface. Big builders of big dish always have to compromise between weight, wind resistance, cost, and so using a solid inner surface and a mesh outer surface, outer layer of panels was a popular compromise for a while. Around the same time, the big dish was built in Arecibo, 1,000 feet in diameter. Here's a contemporary photograph. This was built as a result of a numerical error, and the experiment for which it could have been built could have been done by a 25-meter telescope. But instead, there was a factor which was not taken into account. They scaled it up. It was paid for by the US Air Force, who had all the money they ever needed. And we are left with this wonderful instrument for astronomy. Here's another example of a way around the mass cost problem. This is a telescope in France, still operational, and it has a tilted mirror on the left, quite large, but fixed pretty firmly to the ground. And so a signal will come in, hit the tilted mirror, go off to the right, hit the parabolic fixed mirror, and be focused on the receiver, which is approximately in the center. Back to Cambridge. Now in 1967, I showed this before, Anthony Hewish built a covered 4.5 acres with these dipoles with the help of plucky Cambridge graduate students. The story that Jocelyn Bell Burnell tells is that they did physical labor all summer, the graduate students, and by the end of the summer, they could swing a 20-pound hammer. Well, this interested me because if you know the story of John Henry, which is one of the folk heroes of the United States, what broke John Henry's heart when he competed with the steam drill was him swinging 2 9-pound hammers. And so when I met Jocelyn Bell Burnell a few years ago, I had to ask her about the 20-pound hammer and make her understand that she was outdoing John Henry. She said they didn't swing it very often. But she, being very astute person, noticed when there were some extra squiggles on a chart recorder and took the time and energy to trace it down and discovered pulsars with this array. This array was interesting because it was built in order to study the scintillation of extragalactic radio sources as that passes through blobs in the solar wind. If the source is of small angular size, then it will scintillate rapidly. That is, the intensity of radiation that you see will change with time, in the same way that stars twinkle but planets do not. And so this was originally intended to discover quasars, which would appear as point sources compared to other objects in the sky, but it also found pulsars. In Green Bank, the 300-foot telescope was built in 1962, again about the same time as all of the rest of this, and the 140-foot in 1964. And I'm going to take a brief digression here. In Cambridge, they switched to dishes, again, 25-meter class in 1964 for the so-called 1-mile telescope, an interferometer with a baseline of about 1 mile. And it was starting to map the structure of extragalactic radio sources. The National Science Foundation came on the scene in the mid-1950s and for the first time was a way to fund pure research in the United States. Before the National Science Foundation, the US government had no real way to fund pure research except through the military, and that carried its own problems with it. So the NSF started, one of its first projects was funding radio astronomy, the big instruments needed in special locations. And they chose a region of Green Bank, West Virginia for the first observatory, established the National Radio Quiet Zone around it, which still to this day gives us good protection against sources of interference. And that's why I don't have a cell phone. Let me show you some pictures from the early days of Green Bank. This is a very North American centric review of radio astronomy, but it's limited in time too, so what the heck. The first dish was dedicated in 1958, a 25-meter, still there. The Tatel telescope, there's its control room you see in the right. And if you look in the lower right of the control room photo, you see the punch paper tape that was the storage medium for the data from this telescope. The 140-foot telescope was going to be the centerpiece of US radio astronomy in Green Bank. You can see from the model here that it's a polar mount, which is a horrible choice for a large dish like this. The astropolitical infighting that resulted in the choice of this design is pretty amazing. I don't think there's anything, even in modern politics, the energy and the divisiveness that was going on in these early days is pretty comparable to what we're seeing today. Anyway, the 140-foot was designed around this polar shaft. There's a polar shaft with a person model standing there around which the whole thing would rotate. It had problems with the design of the polar shaft. The shaft was being welded in Green Bank, and they discovered that the steel it was being made of was prone to a brittle stress fracture, so that it could fracture unexpectedly in cold weather. The whole project ground to a halt, and radio astronomy in the US was basically dead. So the astronomers at Green Bank, there were 4 of them, came up with the idea for the 300-foot telescope, a large, cheap instrument that could be built quickly and get radio astronomy in the US off the ground. And I'm just going to show a quick chronology of the 300-foot project, because it's really amazing what you can do if you choose your design parameters correctly. They'd studied design concepts in 1960. On October 1st, 1960, they decided on the transit concept. The project began. They hired an engineer who, between then and mid-November, designed the telescope. Up until March 1961, a few months later, the design was refined. Construction bids were requested in March, and the contract was signed in April, and groundbreaking was in May. By December, the steel work was completed. The surface was attached the next spring, and electronics, and in 23 months, the whole project was done. Here's a quick slideshow of the field where it was built, the groundbreaking. B.D. Linz, who did the catalog of Linz dark clouds, is in this picture, conspicuous in a sea of old white men. But those were the days. And by October, after May, here was the construction and the steel work going up. Very simple design, hoops and ribs. The surface was chicken wire, bought straight from Sears. And here it is in late summer 1962, ready to be outfitted and start observing. You'll notice that it tips down almost to the ground here, which limits its elevation coverage. In order to extend the elevation coverage, they built a ditch. Don't raise the telescope, lower the ground was their motto. And that allowed them to get an extra 10 degrees of elevation or so. And here's its picture in December 1962. The initial surface was damaged, and you can see here it became quite unreliable. And so they did what you and I would naturally think to do. They took it off and rolled over it with a bulldozer. That didn't help at all, and in fact made it quite brittle. So eventually they put a new surface on 10 years later. Lots of improvements. It discovered the pulsar in the Crab Nebula, and this is the discovery image. And what was important about that was it was the first time a pulsar was actually tied to a supernova remnant. Everyone thought that pulsars came from supernova remnants, but this was the smoking gun. It also had the angular resolution able to map out hydrogen far from the center of a galaxy. And although this is not a 300-foot image, the 300-foot hydrogen data showed conclusively that rotation curves of galaxies, as measured by hydrogen, were dominated by dark matter. Here, in fact, are the people that were involved in that study. Mort Roberts at the left, Vera Rubin and her science partner, Kent Ford. Vera and Kent working predominantly at the optical wavelengths, Mort working predominantly at radio wavelengths, but they collaborated a lot on joint projects and pretty much drove home the idea that galaxies have to be dominated by dark matter. The 140-foot telescope was eventually finished. This was the machining of the final ball bearing in Pittsburgh and a mock-up of its passage through a railroad tunnel to come to the Green Bank. And it was discovering things like radio recombination lines, the first long chain carbon molecules in the interstellar medium that Brett talked about, and a pioneer in very long baseline interferometry. While in the early 1960s and mid-1960s, people were doing very long baseline interferometry, combining signals from distant telescopes to really get very high angular resolution. And that led many decades later to the very long baseline array in 1993, still going. There's the 300-foot telescope at its peak. It made the map I showed yesterday of all of those nice objects in the sky. Oh, I got to talk about its end. This is how it looked in November 15th, 1988. And the next morning, it collapsed totally on a calm November night while doing routine observations. Its time had just come. And it's replaced by the Green Bank telescope. Meanwhile, in 1972, this 100-meter diameter fully steerable telescope was built in Germany. You can see again that it's solid inner surface and mesh outer surface. And the Green Bank telescope, many years later, replacing the 300-foot telescope. In 1962, there was an antenna left over from the a space experiment at Bell Labs, and Penzias and Wilson used that to discover the Big Bang. An excess noise temperature, isotropic, unpolarized, free from seasonal variations. The Very Large Array was being planned almost from the moment that NRAO started. It was known that arrays were the way to go, and eventually that the location in a high, relatively dry, relatively flat place of the Southwest was preferable to any place in the East. And so it began operations around 1980. This 27 antennas are reconfigurable. Here they're pulled tightly together, and here they're spread far apart. I'm sure you're going to hear a lot more about VLA and VLA science. It's got this big shed that they do maintenance on, and the antennas are moved along tracks to change from one configuration to the other. Late 90s, not similar at all. This was an array in India that takes advantage of the mild weather of India, so they don't have to worry about ice or snow or any load like that on the dish. And it's made of very coarse mesh and works about up to a gigahertz or two. Can work on neutral hydrogen certainly, and has a lot of collecting area. As Brett pointed out, in the early 1970s, NRAO got into the millimeter astronomy business with the 36-foot telescope shown in its dome here. And this is working at the frequencies where the atmosphere really does make a difference. And so it was placed on Kitt Peak, a modest elevation mountain outside of Arizona, but the site of a lot of optical telescopes. And as Brett pointed out, ushered in the amazing era of molecular astrophysics, which had been not only not predicted, but it had been predicted to be impossible. And so that was replaced, a different surface, and is now, the dome is all that's left of the original now. They're using, I guess, a prototype ALMA dish in its place there. Columbia University got a small dish on the roof of their physics lab, a 1.2 meter dish doing millimeter astronomy. You get a pretty good beam with that, and started mapping the sky in CO in the late 1970s. This is a dish in Spain, their millimeter single dish, the IRAM 30-meter diameter on a mountaintop in Spain. And more recently, a joint University of Massachusetts, Mexico project to design a 50-meter construction, the LMT, Large Millimeter Telescope, on a extinct volcano outside Puebla, Mexico. The project has had its problems, but is finally getting going and is going to be, is producing good things. Millimeter arrays, there were several of them in California, combined into KARMA, which is now defunct, but this opened up the early days of high resolution millimeter spectral mapping. And now we have ALMA, this magnificent array in northern Chile, which is transforming our understanding of millimeter, the millimeter sky, more ALMA. That's a person standing next to one of the ALMA dishes, so you get an idea of the scale. France is expanding its millimeter array, NOEMA. It's going to be 12, 15 millimeter dishes on top of a mountain in Spain. And this is a smaller array in Australia that can actually work up in CO frequencies. Let me say a few words about the future. We all know Future is the name of a rapper out of Atlanta whose debut album, Pluto, in 2012 was extremely well received. There's some future in radio astronomy too. The Square Kilometer Array, a vast international project originally designed to have a square kilometer of collecting area. And so here's a 1999 specification. And the sensitivity is given in terms of collecting area divided by the noise of the receivers. You get more signal by either increasing the collecting area or making more sensitive receivers. The ratio of these is a very good indicator of sensitivity. It was going to go from 150 megahertz to 20 gigahertz. And let's see what else we have here. Well, number of technical things. Anyway, 2 times 10 to the 4th meters squared per Kelvin was the original specification. This turns out, as you might imagine, to be extremely expensive. It was broken into 2 parts, a low frequency in the hundreds of megahertz to work in the desert of Western Australia. This, I believe, is an artist's conception, but work is underway now on that. And then there were several precursors to the Square Kilometer Array. One which is up and running now is ASCAP, a bunch of 12-meter dishes in the desert of Western Australia. They aim for 36 eventually. And ASCAP's real special feature is they have multi-beam receivers that cover a patch on the sky that's illustrated in the lower right. So they have 36 independent beams covering a 6 by 6 degree field of view, and they're doing interferometry on all those. They are starting to produce data now. If you just stay tuned, it should be some spectacular stuff coming out. Meanwhile, the South Africans have built the Meerkat array in the desert, their desert in South Africa, and it's spec to 1 to 10 gigahertz, 64 13.5 meter dishes, and I believe that's going to be expanded with a German contribution to more than 80 dishes in the coming years. Meerkat is up and running. Yesterday, I gave a science lunch talk on hydrogen in the galactic center and got an email in response asking whether I'd be interested in using Meerkat to observe those clouds, and the answer is you bet. Now, the current specs, or as of last year, for the Square Kilometer Array are down by about an order of magnitude, a factor of 20 from the initial, but they have hundreds of millions of euros to build this. So something is absolutely going to happen with the Square Kilometer Array. There's at least a dozen countries that have committed to it. Meanwhile, China has been going its own way and has built this really monster version of Arecibo called FAST, for filled aperture. T is telescope. I can't remember what the S stands for.
500 meter aperture spherical telescope.
500 meter aperture spherical telescope. Thank you, Ryan. And so its diameter is 500 meters. Arecibo is about 300 meters. And here are some photographs of its construction. It's in a karst area of China. So there are these natural bowls that they're taking advantage of. It's built out of these big triangular surface panels. And there you see one being lowered into place. The little figures you see down here, the blue spots are the hard hats on the workers. So that gives you an idea of what the scale is. And there it is, finished now. And the first science is starting to come out of FAST, a truly amazing instrument. Arecibo has a complicated optical system with a secondary and tertiary subreflector that is hung above the main spherical reflector in order to bring the radio waves into focus. FAST, and here's a picture of that for Arecibo, it's got a 25 meter dish upside down in this dome. FAST is doing something very different. They have a very simple cabin up here that illuminates, looks at this part of their spherical dish, and their spherical dish is active, and we will be pulled into a parabola on that area. And so they are moving a parabola across the spherical reflector. That is going to be pretty amazing when it gets working. It's sort of working now. I want to say that this is an interesting dish built in Canada to study very highly redshifted hydrogen. And it is 80 meters by 100 meters, made of 420 by 100 meter segments there, working 400 to 800 megahertz. And during the time of construction of this telescope, its scientific rationale changed completely with the discovery of fast radio bursts. And this now is the world's premier instrument for studying fast radio bursts. It's probably discovered, what, a couple hundred of them now, including some important fast radio burst repeaters, which are really important. And from what I've heard, it's not even clear that it's going to be able to do its primary, what used to be its primary scientific objective. But if there's one lesson to be learned from the history of radio astronomy, it's that if you build a big sensitive instrument, the science will open up to you in ways that you couldn't have imagined. And CHIME is now a very important instrument on the world scene. And they are planning to put outriggers in California and at Green Bank to start doing interferometry on some of these fast radio bursts. The big kid on the block is the next generation VLA. And this is a project started just a few years ago, but has tremendous momentum now. And this is to have a series of small dishes, I think something like 350 of them, scattered about the southwest of the United States. And so what you're seeing here on the top is the general outline of the stations. These stations may contain multiple dishes, and this shows the reaching down into Mexico and over into an important congressman's district in Texas. And then if you look at the spirals here are on the scale of 20 kilometers. So this is on the scale of hundreds of kilometers. This is on the scale of tens of kilometers. There are these spiral patterns. And on the scale of a half a kilometers, there's a kind of random pattern here. That shows how it goes with the outriggers at the locations of some of the VLBA sites for very long baseline interferometry. An artist's conception of what the dish might look like, 18 meters. Oh, I have down 214 dishes is the current design by 18 meters. They're working on this very fast, and this will be an amazing, amazing instrument when it's completed. I wanted to finish by just saying a word about work in space. It is very, very, very expensive to go into space. I once calculated, what was it? You could, for the cost of the Hubble Space Telescope, you could make 50 Green Bank telescopes and operate them for 100 years. So this is the Radio Astron 10 meter. It was designed for very long baseline interferometry between it and stations on the ground and telescopes on the ground, and just completed its life exactly a year ago. And it is a small radio telescope, 10 meters. But I have on its surface the footprint of the Hubble Space Telescope to show you the relative small size of things that we've been able to put in space. And we all know that the total cost of Hubble is probably $15 billion, something like that, over its lifetime. And so it's just very expensive to go into space. But there are plans for space missions, and this is one of them. DARE, it's to look at extremely low frequency hydrogen, highly redshifted from the epoch when the universe was dark and then started to be reionized by the first generation of stars. And the important thing about this instrument is it's going to work from the backside of the moon. It's going to use the moon as a shield from interference on Earth, and that's its rationale for going into space. DARE is not funded yet, but they're still working to try to get it going. So let me end up with a photograph from Green Bank and take any questions. I'm sorry for this brief high-speed tour, but there's a lot to cover. Thanks.
All right, thanks, Jay. We are running a little bit late, but we have time for one question if there's anything left. There's already a few that we were answering in the chat window. If not, then Tony Minter is on the schedule to give us a little bit more detailed talk about the GBT, but he emailed me saying that he was having some internet problems, and I have seen him kind of pop in and out of the meeting. So I think that his internet's not quite up to speed today. In which case, I will go ahead and give the talk for Tony. because I do have his slides, and we will kind of make this a little bit more abbreviated. So thank you, Jay.
Okay, bye-bye.
Ryan, I'm ready to go now if you want me